So here's a fun puzzle to try out. Let's say a family is going on a road trip and they have 8 kids. The kids are all 1 year apart and the youngest is 1 year old. So we're just going to name them by the numbers. So there's 1, 2, 3, 4, 5, 6, 7, and 8. And their vehicle, let's say it's a minivan, has a kind of peculiar seating chart. It looks like this. These are the seats, not including the seats for the parents. So the rule is no 2 kids can sit next to kids that are 1 year older or 1 year younger. So they have to be separated, otherwise they're going to get into a fight and the trip is going to be super long and annoying as it is. So we want to make sure that it's as peaceful as possible. So for example, 2 cannot sit next to 3 or 1. So next to means like this. These are all the lines. So this one here is next to this one, this one, this one, this one, this one, and this one. So how do we do it? And I'm going to let you play around with it. If you just try guessing and putting random numbers in there, it's going to be difficult. The problem is that we have 8 choices for the first one, 7 for the second, 6 for the third, 5 for the fourth, 4 for the fifth, etc. So that comes out to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 different ways of arranging all the kids in these seats. So that we use the shorthand with the exclamation point there. It means factorial. So 8 factorial is equal to 40,320 different ways that this puzzle can be arranged. So randomly guessing is not a good strategy. You have about a 0.025% chance of getting it right. So you're going to need to use reasoning and logic to try to figure out the correct seating arrangement. And I'll tell you right now, there's actually 4 ones that'll work, but they're mirror images of each other. So if you can find one, you found the other 4. And go ahead and give it a go, play around with it, and see if you can find any rules when you start putting it on there. And if it's difficult, remember, try in a smaller case, a simpler case. So for example, let's say we want to arrange one through 4 in a seating like this, and these are the connections here. So you can see if you start playing around with it. By the way, this is a hint. I'm not going to give you the answer yet, but go ahead and try to solve the original one if you want. So one thing that we notice is that 1 has only 1 restriction. It can't sit next to 2. But 2 has 2 restrictions. It can't sit next to 1 or 3. Same thing with 3. 3 can't sit next to 2 or 4. But 4, like 1, has only 1 restriction. That's 3. So the ones with the least amount of restrictions, it makes sense to put them up. Well, let's look at the positions we can put them in first. So this one only has one neighbor. The second circle has 2 neighbors. The third circle has 2 neighbors. And the last circle has 1 neighbor. So there's a clue right there. So one way we could order this would be to put the ones that have the most restrictions on the outside. So we'll put 2 and 4 on the outside like that. And we can see then that 3 can't go here. Wait a minute. Jeez. I made a mistake. Here's the seating chart again. So we can see that 1 and 4 have the most. So let's put them on the inside. We could also put the 2 and the 3 on the outside, but accidentally we're a 4. Anyway, so now we can see, well, we have one space here, and we can't use 2 because it's next to 1, so we'll put 3 there. And then we can put 2 here. And that solves the seating arrangement here. And we can also write it like this: 2, 4, 1, 3. And it's the same thing, basically. It's a symmetric answer. So does that give you any clues about how to solve this first problem here? Well, here's how I would do it. By the way, come back if you want a chance to solve it yourself. Spoilers ahead. So we notice the same thing we notice here. 8 and 1 only have one restriction. 1 can't sit next to 2, 8 can't sit next to 7. All the rest of them have 2. And if we look at the seating chart here in the minivan, we notice that this circle here has 1, 2, 3 neighbors. So we'll just write that here. And the same thing with this one. Now, this one on the outside has 1, 2, 3, 4. Same for this one, same for this one, same for this one. And the inside ones here have 1, 2, 3, 4, 5, 6 neighbors. So we're going to write that here. So the ones with the most neighbors should be the ones that can sit next to the most others, the most other kids, which would be 8 and 1. So we can just choose whichever one we want. Let's say we'll put the 1-year-old here, we'll put the 8-year-old here, and now we should figure out where 7 and 2 go. So I'm going to cross out 1 and 8. So 7 and 2. Obviously, 2 cannot go there. So 2's got to go here, and 7 will go there. So now we've got 4 kids seated. Now the next one is kind of arbitrary. You can pick whichever one you want to start with. So let's put 3 right here. So still good. 3 is next to 7, 1, and 8. We're good. Now, which one of these ones could we choose? We could choose 5 or 6. Definitely not 4. If we choose 6, let's say we put 6 here, we're going to have to put 4 and 5 over here, which isn't going to work, right? So we're going to have to put 5 over on this side. 5 goes there, and now we have 3, 5. We have 4 and 6 left. Okay, does it matter how we pick those? Well, we can't put 6 here because there's 7, so 6 has got to go here. And finally, we have 4. And are we good? I believe so. So the other answers to this are mirror images. So we can flip, if this is the mirror axis this way, we can flip 4 and 6 and 3 and 5 and put them on the opposite sides. So that would look like this: 7, 1, 8, 2, 4, 6, 3, 5. I'm not going to draw the seats. Now, the other thing that we can do is flip this way. So we can put 2 on the top. We can put, if we put 2 on the top, then the mirror image would be 2, 8, 1, 7. And then we would have 3, 5, 4, 6. Is that correct? I don't see any errors there. And then again, we can flip these to the opposite direction. So 2, 8, 1, 7, and then 6, 4, and 5, 3. So these 4 are our solutions. Did you figure out the answer to the problem? It's kind of a tricky one, a little bit. There's definitely some reasoning that it takes to figure out the solution to the problem. And if you get stuck ever, don't worry about it. It's not a race. A lot of math problems take years, decades, centuries, honestly. And so it's okay to just, not rush through it, figure out what you can, take a break if you want to, think about it. and then come back to it later and see if you can make any headwind. So, how is this related to mathematics? You might be asking. Well, we touched on a few things. One, there's a whole field of called combinatorics that is basically how to figure out massive numbers, counting numbers. So like all the different possibilities that we could have gotten here is using this technique called combinatorics, and it's a massive active field of mathematics to this day, and it is great for counting very complicated things. It's very fancy counting. And also, we did briefly look at probability. Basically, once we figured out the combinations that there could be, we divide that by, we divide the number of solutions by that number, and that's how we get the probability. So 4 out of 40,320. And the whole puzzle itself, just trying to figure out who sits where, is actually a field of mathematics called graph theory. And you could get a PhD in subfields of graph theory. It is incredibly useful and an active field of mathematics right now for solving everything from computer networking to chemistry. It's really amazing, and you probably won't even see something like this until you're maybe in advanced undergrad, or might not even see it until grad school. But I mean, why wait? It's amazing. And there's a lot of practical uses for it too. We just figured out a seating chart. I heard a story from somebody who's actually has a PhD in graph theory, and they used it to figure out the seating arrangement for their wedding, to make sure that everybody was sitting with people they liked, and so anyway, it's very interesting, active field of mathematics. All right, thanks. Bye.